Hello and welcome to Aditya classes, where we have been discussing about assignment using Hungarian method. Now till this point we have taken a couple of questions where first we learned how assignment is done, what exactly an assignment problem is, how assignment is done. Then in second video we saw what happens when there is a degeneracy in assignment problem. What is the state of degeneracy? Where number of assignments are less than number of rows or columns. For example, if you have 5 rows, definitely you will have 5 columns. And if your assignments are less than 5, that is a state of degeneracy. And then how do we resolve that degeneracy? Today we'll take up a question where we will try to maximize the given problem of assignment. So this is an assignment problem, but instead of minimizing, the default method where we were going for row reduction and column reduction was for minimization of an assignment problem. Today what we'll try and do is, we'll try to maximize this given assignment problem. Now how do we maximize it? First, let us understand that whatever algorithms we have studied, may it be simplex, may it be transportation, may it be game theory, they all are built, they have certain assumptions. Now if we try to change them, for example in simplex, we have learned Cj minus Zj. Now if Cj minus Zj is always for maximization. If you ever come across minimization, then what do? Instead of changing everything, we just take Zj minus Cj. So there is an alternative. Our natural flow in simplex is go for Cj minus Zj for maximization. If you come across minimization, change Cj minus Zj to Zj minus Cj. That is our adjustment over there. Here in transportation and assignment, what we do is, our default algorithm is for minimization of problem. We are using Hungarian method. Assignment using Hungarian method. So the default method will give me minimum solution. But this time the question is to maximize. It might so happen that whatever numbers are given over here, these are not costs, these are other profits, these are gains, these are sales. Now if these are profits, if these are sales, if these are gains, I definitely want to maximize them. But if I try to solve it using normal assignment problem, then it will get minimized. I'll get minimum profit, I'll get minimum sales. So here the important thing is maximize the given problem. Now let us give them some names. We have A, B, C and D for sources, P, Q, R, S for assignment. Maybe it could be salesman to territory, it could be jobs to machines, it could be workers to machines, it could be workers to jobs, whatever. If we want to call it, let us call it workers to machine. It might so happen that if worker A is positioned at machine P, he can get me a profit of 25. On Q, he can get me a profit of 38. On R, he can get me a profit of 43. On S, he can get me a profit of 20. So what is the best possible assignment for worker A? Definitely 43 is the best. Worker A should go to R, machine R. Then he'll give me maximum profit. So we'll try to assign this complete, but keeping in mind that we wish to maximize. Now let us understand a small concept over here. We'll take a very small question. Let us say 3, 7, 9, 11. Given a chance, if you want to minimize the cost, what would be your first choice? Let me call it A, B, C and D. Given a chance, if you wish to minimize the cost, what will be your first choice? Your first choice will be AC, because this is the least cost cell. Second choice would be AD, because this is okay, not as good as 3, but better than 9 and 11. So your first choice would be AC, second choice would be AD. We are just trying to understand a concept. This is not solution of this problem. We are trying to understand one concept that will be following over here. Third choice would be B to C, because this is 9 rupees. Third choice would be B to C, and fourth would be, last one would be B to D. Given a chance, these would be my selections. This would be the priority of my selections. to minimize the problem. Now, if I tell you that these are the profits, I wish to maximize them, then what would be your first choice? Your first choice would be 11 rupees, BD. Second choice would be 9 rupees, B to C. Third choice would be A to D. And final choice would be A to C. So this will be my sequence if I am trying to maximize my return, and this would be the sequence if I am trying to minimize my returns. Now, if we look at these priorities, you will see AC, AD, BC, BD, AC, AD, BC, BD, exact reversal of my priorities. AC is first priority, here it becomes fourth priority, AD is second becoming third, third becoming second, and fourth becoming first. So there is an exact reversal of my priorities. So I can say that maximization and minimization have a complete reverse relationship. A complete reverse relationship. What is my best choice in minimization becomes my last choice in maximization. This we need to keep in mind, that they carry a completely opposite relationship. But my assignment algorithm is such that it will always give me this priority because it is designed to give you minimum solution, minimum cost. So it will always give you this solution. Then how do I maximize? What algorithm do I use? For that, what I'll do is I convert the profit matrix into loss matrix. What do? I convert this profit matrix, because this time it is profit, I wish to maximize it. If it were a minimization problem, fine, solved. But if it is a maximization problem, then I am in a fix. I need to maximize it, but my algorithm will give a minimum solution. So what I do, I convert the profit matrix into loss matrix. How do I go about that? I select the maximum from complete matrix, all costs, maximum is this, and subtract all values from 11. So 11 minus 3 would give me an 8, 11 minus 7, 4, 11 minus 9, 2, 11 minus 11, 0. Now why is this loss matrix? Because 11 is the best choice, and if you select 11, then there is no loss. There is a loss of 0 units. 11 is best possible profit, but if you pick a choice of 9 rupees, then there is a loss of 2 rupees. Because 11 was the best possible, but you somehow made a mistake and you selected 9. So when you selected 9, your loss is 2. Because you could have made 11 rupees, but now you are making only 9. So there is a loss of 2. Here, if you are selecting this 7, you could have made 11 rupees, but now you are making only 7 rupees. So there is a loss of 4 rupees. You could have made 11 rupees, but you are making only 3 rupees. There is a loss of 8 rupees. So what I have done is I have converted the profit matrix into loss matrix. Let me call it profit matrix, and this is loss matrix. I have converted profit matrix into loss matrix. Now what I'll try and do is, I'll try to go for assignment. Suppose this is a new question. This was my profit matrix, I have converted into loss matrix. Now, if I talk of losses and give this question to my assignment algorithm, what it will try to do? It will try to minimize the losses. Here it was trying to minimize the profits, which is not a good idea. So I converted my profit into loss, and now I am asking assignment algorithm to solve this problem. So again it will try to minimize it, but in turn to trying to minimize it, it will actually give me better results. It will be minimizing the losses. So now if I subject this to solution using matrix method, what will be my best choice? I have A, B, C and D. What will be my best choice? 0. That is, first choice will be BD. Second choice will be, smallest is 0, First choice making BD. Now I'm trying for assignments. Second, BC, because this is second smallest. Smallest is definitely 0, but then okay, 2 is good. Then 4 is good. So third choice for assignment, for minimization of this problem would be AD. Fourth choice for minimization of this problem would be AC. So what I have done is, I have minimized my problem, but ultimately I am getting same priority as the maximization case. BD, BC, AD and AC. So this would be the idea behind maximizing the problem. What we'll do is, instead of going ahead and maximizing this problem, what I'll do is, I'll invert the matrix. I'll convert the profit matrix into loss matrix. Obviously, this has to be a profit matrix or a sales matrix because we are trying to maximize it. I'll convert this profit matrix into loss matrix, and then simple assignment would do. So let us go ahead and remove this, and we'll try to solve this assignment problem using Hungarian method, and we'll try to maximize it. So what would be my first step? First step is convert profit matrix into loss matrix. I'll convert this profit matrix into loss matrix. How? Subtracting all cell values from largest in all cell values. Let us prepare a blank matrix where we will transfer those values. What are we calling them? A, B, C and D, P, Q, R and S. Convert profit matrix into loss matrix. This is a profit matrix, I'll convert it into loss. Subtracting all values from maximum. Maximum is 43, now maximum is 45. Maximum is 45. Ultimately, maximum value in this matrix is 45. So subtract all values from 45. 45 minus 25, 20. 45 minus 38, 7. 45 minus 43, 2. 45 minus 20 would be a 25. Then we have 0, 33, 26, 41. Then we have 2, 29, 16, 21. Then we have 9, making it 36, 5, 0 and 1. I have converted my profit matrix into a loss matrix. Let us have a quick check if these values are correct. It should be a 27, 2 and 25. Then this should be 0, 33 and 26 and 41. Then this should be 2. Then this should be 29, 16, 21. We have a 36, 5, 0 and 1. So this is my loss matrix. Now you can go ahead and minimize it. How do we minimize it? First step was convert profit matrix into loss matrix. Second step is row reduction, or you could go for column reduction, it hardly matters. But the idea is we need to go for both row reduction and column reduction. Let us prepare an empty matrix and then we'll go for row reduction and column reduction. Here is our empty matrix. Row reduction is subtracting minimum of all from all. in each row, in each column, for row reduction in each row, I'll subtract minimum from all values. Minimum is 2, subtract it from all values. Remember, in converting profit matrix into loss matrix, we picked up the maximum, and from that maximum I selected subtracted all. But for row reduction, column reduction, what we do is we select the minimum. For converting profit matrix into loss matrix, we select the maximum and subtract all. But here we select the minimum and subtract it from all. So it will be an 18, 5, 0 and 23. In this row, 0 is minimum, subtract 0 from all, giving me 0, 33, 26 and 41. In this row, 2 is minimum, subtract 2 from all, giving me 2, 27, 14 and 19. Here 0 is minimum, subtracted from all, 36, 5, 0 and 1. So now this matrix is row reduced. After row reduction, each row should have at least one 0. First row has a 0, second row has a 0, third row doesn't have a 0. Oh, this should have been 0. We have subtracted 2 from all, making it 0, 27, 14 and 19. It has a 0, fourth row has a 0. So this is always a good idea to check, because we put 2 over here by mistake. So now while checking it, we realized that this should have been a 0. So after row reduction, each row is having at least one 0. What were their names? Their names were A, B, C and D, P, Q, R and S. This was our second step. Let us go for our third step. Third step is row reduction done, column reduction. So after column reduction, I should be having a 0 in each column. This is the idea behind reduction. After row reduction, I have a 0 in each row. After column reduction, I should be having a 0 in each column. If you check the row reduced matrix, that is this matrix, every row is having a 0, but not every column is having a 0, because it has not been reduced for columns P, Q, R and S. Each row is having a 0, but not every column is having a 0. This column is having no zeros, this column is having no zeros, because it has not been column reduced. So let us go ahead and column reduce it. Column reduction, again, subtract minimum in each column from all other values. Minimum is 0, subtracted from all, will get an 18, 0, 0, 36. Here 5 is minimum, so we'll get 0, 28, 22 and 0. Here we already have zeros, so subtracting zeros from everyone, 0, 26, 14 and 0. Here 1 is minimum, so we'll get a 22, 40, 18 and 0. So now this matrix is row reduced and column reduced after third step. In routine assignment, this becomes our first step, row reduction and column reduction. But because this was a case of maximization, first I need to go for converting profit matrix into loss matrix, and now we can go ahead and solve it. So this is our column reduced matrix. Each column is having at least one 0. Now you can go ahead and make assignments. What preferably should be the priority for assignments? If you remember from our previous videos, first priority should be unique 0. Unique 0 is alone in its row and column. If you do not find any unique zeros, second priority should be single 0. What do we mean by single 0? Single 0 either in row or column, alone in its row or column. Difference between unique and single is this is alone in its row and column. This is alone in its row or column. So first of all, you should look for unique zeros. Second, you should look for single zeros. If there are single zeros, go ahead and assign. If there are unique zeros, go ahead and assign. And if you do not have either of these cases, then look for minimum zeros in row or column. These are the priorities for our assignment. So first let us scan for unique zeros. UNIQUE, unique zeros. Unique zero. This is a zero, but it is not unique because it has someone in its row. This, no one in row, but there is a zero in its column, so it is not unique. This is also not unique because there is someone in its row. This is also not unique because, okay, it is alone in its row, but then there is a zero in its column, so it is not a unique zero. These three cannot be unique because they all have each other. So the idea is there is no unique zero. We have no unique zeros in our case. Then single zero. What is single zero? Alone in its row or column. This time I am not looking for row and column. If we have a look at this zero, this was alone in its row but not in its column. Here I need alone in its row and column. Row is satisfied and column is not satisfied. But now I am looking for single zeros. This is not a single zero because they both have each other. If I look at this zero, yes, this looks like being single, at least in its row, either in row or column. This is single in its row. So I can assign it. And whenever I make an assignment, it has to be unique. Alone, here there is someone else. Let me cut all zeros. Whenever an assignment is made, ultimately it should be a unique. Assignment is always made in unique zero. Now because we were not having any unique zeros, what I did? I looked for single zero and made it unique by removing other zeros. So we are through with our first assignment. Now if I move to C, there are no zeros, leave it. If I move to D, there are in fact 3 zeros. So we'll leave it. We are looking for single zeros. Now let me move to columns. This column is done. Here I have 2 zeros, leave it. Here again I have 2 zeros, leave it. Here I have single zero. At least column wise it is single. So I'll make an assignment and what I'll do, I'll remove other zeros. Now this assignment is also unique. We have a unique assignment. So then, now let me scan it again. We are through with all rows, we are through with all columns, but not all assignments have been made, not all zeros have been assigned. So let me check. Let me go to first row. 2 zeros, leave it. Assigned. No zeros, assigned. No zeros, at least in its row. Now this has become single. Earlier it was not single because there was a zero over here also. But now column wise it is single. Row wise it is not. Column wise it is single. So I can make an assignment over here. I make an assignment, I remove the other zeros. Now it is a unique zero. Although it was having zeros in its row and column. But now because they have been cut, in the surviving terms, it is a unique zero. There are no other surviving zeros. Now I am through with second column, third column, fourth column. Now you can have a good look at this matrix. There are no further zeros remaining in this. So once again, we are stuck with degeneracy in the problem. And what is the way to resolve this degeneracy? We cut all the zeros with minimum possible lines, either horizontal or vertical. And not minimum possible lines, rather number of lines equal to number of assignments. You have made 3 assignments, so you have 3 lines. You need to cut all zeros within 3 lines. Why 3 lines? Because you have made 3 assignments. You get n number of lines, where n is equal to number of assignments. I've made 3 assignments. I should have made 4 assignments. This is a case of degeneracy. You need to cut all zeros using horizontal or vertical lines. So let me go ahead. This idea is select the one with maximum zeros first. This is cut. Our previous video was on degeneracy only. So if you have any doubts how degeneracy is resolved, how we proceed further, you can check that video. Here what I'll do is, I'll go ahead and solve the degeneracy. Here I have 2 zeros, I can make this line, then I can make use of this vertical line. All zeros in this matrix have been cut by either a horizontal line or a vertical line, and only 3 lines, because there were only 3 assignments. Now I am left with these uncut cells. There is a rule for transferring this matrix to new matrix. Whenever there is degeneracy, there is a rule to transfer it to new matrix. What is that rule? First rule is subtract minimum from all uncut cells. Subtract minimum from all uncut cells. From all uncut cells. Whatever is minimum in uncut cells, subtract it from all uncut cells. Second rule is add that value to intersections of lines. And third is copy all the cut cells. So there are 3 kinds of cells over here. One is uncut. Another one is where there are intersections of lines. So we have uncut cells, we have cut cells. Uncut cells, these are cut cells, and these are intersection cells. So I have 3 rules. And using these 3 rules, I'll transfer these to my next matrix. And my next matrix would be, let us prepare an empty space and then we'll see what happens next. We have another detailed video. The previous video was on degeneracy. So if you have any doubts regarding degeneracy, you can check out that video, P, Q, R and S. Now the rules are subtract minimum from all uncut cells from all uncut cells. Minimum in all uncut cells is, let us make this one as in and the other one as from. Subtract minimum in all uncut cells from all uncut cells. Minimum in all uncut cells is 14. So we will be subtracting 14 from all. Subtract 14 from all uncut cells, making this one as 14, 12, 26, 4, 0 and 8. First step is done. Subtract minimum in uncut cells from all uncut cells is done. Add that value to intersections of lines. 14, that value. 14 is that value, minimum value, to intersections, to these 2 places. 18 plus 14 would become 32. 36 plus 14 would become 50. And then copy the remaining cells. If I copy these, this is a 0, 0 and 22. Then these are a couple of zeros. Then we have 3 zeros over here. This is my new matrix. This is a next iteration. These were steps, but because this was degenerate solution, this is my another iteration. Now let me go for assignments. We need to look for unique zeros. 2 zeros, so it is not unique. Looks like being single in its column, a row, but not in its column, so not unique. 2 zeros, so not unique. 3 zeros, so they cannot be unique. Unique is alone in its row and column. 2 zeros, not unique, not unique, not unique. This is not unique. None of these are unique. So let me go for single zeros. 2 zeros, leave it 1 0. At least row wise it is single. Let me remove the column zeros. Now it is unique. Nobody in its row, nobody in its column is 0. C, we have a single 0. Make an assignment, make it unique. We made it unique. D, there are 2 zeros, leave them. Remember, 2 zeros, leave them. I am looking for single zeros. This is a point where things can go wrong. If I select this 0, both these zeros will get cut and you will be left with 3 assignments. So follow the rules, unique, then single. This was single, I made it unique. This is not single, these are 2 zeros. All rows are done. Let us scan columns. Done. 2 zeros, leave it. Done. 1 0. It is a single 0. Column wise it is single. Remove all zeros in its row. Now it is unique. Done. So I've done all, I'm done with all columns, but still there are some zeros. Let me start again with rows. First row, single zero. This time it is a single zero. In fact, it is a unique zero. Nobody in its row, nobody in its column is a zero. Now I have 1, 2, 3 and 4 assignments. So this is my final assignment. But remember, this is not an assignment for maximization. Rather, it is an assignment for minimization of my loss matrix. But I need to maximize that. So what I'll do, I'll superimpose my results to the original solution. What were my results? B to P, A to Q. B to P, A to Q. Then there is C to R and D to S. C to R and D to S. So now do you understand the sequence? We were given this problem to maximize it. I converted this profit matrix into loss matrix because assignment only knows one thing. It only knows how to minimize things. But profit cannot be minimized. Profit needs to be maximized. So I converted this profit into loss. Now assignment will minimize this also. And in turn, what is it doing? It is minimizing the losses. So this was a loss matrix, row reduction, column reduction. There was degeneracy. We resolved this degeneracy using 3 lines because of 3 assignments. These were the sequences. We have our new matrix and this time we have a final assignment, feasible assignment, optimum assignment. But this assignment is for minimization. So what I do, I overlap this solution to my original problem, giving me my maximum solution. So what will be my maximum solution if I try to put it over here? We do not have space. I'll try to put it over here. What will be my maximum solution? A to Q at 38. Then there is B to P at what? 45. Then there is C to R and D to S at 29 and 44. Total how much? This will be 9 and 4, 13, 13 and 5, 18, 18 and 8, 26. 2 carried, 4 and 4, 8 and 2, 10, 15, 156. This is the maximum profit that you can make from this given problem. Let me check if it is correct. 40, 80, 100, 130, 8 and 5, 13, 13 and 13, 26. Fine, 156. So this is the maximum that you can make from this. Sequence was converting profit matrix into loss, row reduction, column reduction. If degeneracy comes, resolve it using this and then finally superimpose the results onto your original matrix. Because this was a converted matrix. This is not our original matrix. So I superimpose my results onto my original matrix. This is how we solve a case of maximization in assignment. Next time when we meet, we'll pick up more cases of assignments. So this is it for our present discussion. Until we meet next time, do take care. Thanks for watching. Bye-bye.